Imagine taking a humble lump of earth and reversing nature's weathering process to forge a brand new stone. Making ceramics by firing clay is essentially a reversal of the natural weathering process of rocks. Long after our ancestors first mastered fire, ancient potters learned to harness this elemental force to reshape the earth itself. However, inside the intense heat of early kilns, a hidden microscopic battle raged, the ultimate struggle between thermodynamics pushing for chemical equilibrium and kinetics freezing these reactions in time. Welcome to the fascinating world of ceramic phase evolution, where every ancient vessel is a kinetically frozen artificial rock that holds the deep secrets of humanity's evolving pyrotechnology.
When firing clay, a potter attempts to reverse a natural geological process. Over millennia, solid rock weathers, fractures, and dissolves into soft, waterlogged clay mud. The goal of early pyrotechnology was to force those separated chemical compounds back together, using heat to forge a hardened, artificial rock. But human and earth heat differ vastly. This shows the microscopic structure of diabase and gabbro, two natural igneous rocks. Because geological cooling takes millennia, reactions reach completion. You can see large, clearly defined crystals of clinopyroxene and plagioclase reaching absolute thermodynamic equilibrium. Ancient potters had hours, not millennia. This electron microscope scan shows Roman terra sigillata, fired to roughly 1,000 degrees Celsius. Compared to natural gabbro, the structure is chaotic. It is heavily vitrified, dissolved into glassy sheets with an incomplete, messy crystal fabric. Because the firing cycle is so short, the clay never reaches equilibrium. Reactions abort mid-process. An ancient ceramic is a kinetically constrained, frozen state of disequilibrium. To understand why these reactions freeze, we have to look at the physical reality of the earliest human firing technology, the simple pit kiln. Pottery is stacked in a hole, covered by combustible material. This design is inefficient. The earth insulates the bottom, but fuel must sit on top so burning logs don't crush the pots. Consequently, most heat simply escapes upward into the open air. Because of this extreme heat loss, these early structures operated at relatively low temperatures. A pit kiln rarely exceeded 1,000 to 1,200 degrees Fahrenheit. Geological rocks cool along a steady curve over millennia. A pit firing is a sharp, hours-long temperature spike. The heating curve is steep, and the hold time, the period where the kiln maintains peak temperature, is exceptionally brief before cooling begins. Heat provides the thermodynamic license for a chemical transition to occur, but time governs the speed. In a pit kiln, kinetics exercises ultimate control by cutting the clock short. To measure exactly how far short early ceramics fall from perfect equilibrium, we first have to map out what perfect equilibrium actually looks like. We use the Gibbs Phase Rule. This is a mathematical formula that dictates exactly how different mineral phases will coexist within a closed system at specific temperatures and chemical compositions. This chart visualizes that rule for a binary system, a mixture of exactly two minerals, a northite and diopside. The horizontal axis plots the chemical composition ratio, and the vertical axis plots the temperature. Those two curved lines sloping downward are the liquidus curves, marking the exact temperatures where the mixture begins to solidify. Where they meet at the bottom center, at exactly 1270 degrees Celsius, is the eutectic point. This is an invariant equilibrium state. It is the lowest possible melting temperature where the two solid mineral phases and a liquid melt perfectly coexist. Watch what happens to a hypothetical melt as it cools. The mixture starts near the top left, completely liquid. As the temperature drops and hits that liquidus curve, crystals of solid anorthite begin to precipitate out. Because solid anorthite is being removed from the liquid, the chemical ratio of the remaining melt constantly shifts, sliding the system further down the curve. Eventually, the cooling melt hits the eutectic temperature floor. At this exact coordinate, all remaining liquid instantly freezes into a highly ordered, layered microstructure. This mathematical, highly predictable phase evolution is exactly what would happen to a lump of clay if a potter's kiln could operate at extreme heat for an infinite amount of time. But raw clay dug from the earth is chemically complex. By adding a third component like quartz, the binary graph expands into a three-dimensional ternary phase diagram. We now have complex curved liquidous surfaces sloping down from three sides, converging into a single ternary eutectic point deep in the center. This diagram maps the calcium oxide, alumina, and silica components found in the actual raw clay used for Roman terra sigillata. That specific black triangle marker represents the clay's exact chemical makeup. At equilibrium, a mixture in this zone will stabilize into three distinct phases: wollastonite, anorthite, and silica. However, early potters never melted this raw material completely. Without a liquid phase to physically speed up mass transfer across the entire vessel, global equilibrium is impossible. Instead, the ceramic relies on local microequilibria. If we zoom into the clay matrix, we see individual mismatched mineral grains physically pressed together, calcite touching quartz, quartz touching illite. Because the firing is so brief, chemical reactions can only occur locally, right along the microscopic borders where these differing grains physically touch. These rushed border reactions create anomalies like the Gehlenite problem. Based on strict thermodynamics, an aluminum-rich pyroxene phase should form at these specific boundaries, but it rarely does. A completely different mineral, Gehlenite, forms instead. According to Goldsmith's rule of constellation, Gehlenite's specific molecular structure requires less activation energy to nucleate. Kinetics favors the easier path over the perfect one. Every fired shard of ancient pottery is a mosaic of thousands of these aborted microreactions, permanently frozen mid-process the moment the potter cut the heat. Temperature and time dictate the phase evolution, but ancient potters learned to control a third, invisible variable, the flow of oxygen through the firing chamber. A simple updraft kiln pulls massive amounts of external oxygen directly into the fire. This creates an oxidizing atmosphere, which drives standard, predictable chemical reactions within the clay. As communities grew, potters built large, fully enclosed beehive kilns to fire massive volumes of work at once. Because the fire and the pottery were enclosed inside a brick chamber, potters could physically block the external oxygen supply by closing a damper at the top flue. This created a reducing environment. Inside a sealed, burning kiln, carbon monoxide and carbon dioxide violently compete in a process called the boudoir equilibrium. The fire is rapidly starved of free oxygen. When a fire can't get oxygen from the air, it finds it somewhere else. These charts compare mineral stability under an oxidizing environment on the left and a reducing environment on the right. The starved fire chemically steals the oxygen it needs directly from the metallic oxides locked inside the solid clay. Look at the red calcite bars across the two charts. Stripping oxygen from the kiln alters the entire phase stability. In the reducing environment on the right, calcite resists thermal decomposition to temperatures roughly 100 degrees higher. By simply opening or closing a physical hole in the kiln roof, the ancient potter was actively rewriting the thermodynamic rules of the firing cycle. The most visually dramatic result of this oxygen theft happens to the iron oxides distributed throughout the clay matrix. An oxidizing fire leaves iron fully saturated, producing rust-red hematite, but a reducing fire violently strips the oxygen atoms away, leaving behind a deep black mineral called magnetite, allowing the creation of vessels like these. Athenian master potters manipulated this exact fugacity transition. By deliberately choking and reopening the oxygen supply during a single firing cycle, they forced both chemical states to exist on the same vessel, producing precise, contrasting red and black artwork. Crucially, this transition leaves a permanent physical signature. This chart tracks the magnetic susceptibility of fired clay. The bottom curve shows the baseline for oxygen-rich clay, but look at the top curve tracking the reducing atmosphere. The magnetic response experiences a massive exponential spike. Because the stripped magnetic is highly ferromagnetic, it permanently alters the magnetic profile of the clay. The physical magnetic susceptibility of the shard acts as a permanent, readable data log of the exact atmosphere inside the ancient kiln. An ancient pot is a highly complex, frozen thermodynamic record, a crystalline snapshot of the exact moment human intervention interrupted geological time.